measure the paths of planets and what's going on. Just a few things I want to go over. What you can see here, what you guys just did is essentially what some of those early astronomers were doing when they were figuring out where Earth was in the solar system and also trying to establish the laws of the planetary rotation. So we very carefully measure the paths of the planets. And just to point out, I might have said this last time, but the word planet comes from the Greek word for wanderer. So those planets kind of wander throughout the stars as they go around their orbits. And the two questions I wanted to just talk about a little were those last two, discussing why Mercury and Venus are kind of shifting back and forth so often. And that's because Mercury and Venus are the two inner planets. So as they travel around the sun, they're actually they're going a lot faster than Earth. And we see them move away from us around the sun. And then for a while, it looks like they're kind of catching up to us as they start to lap us on their orbits around the sun. The outer planets, Uranus, Neptune, Jupiter, and Saturn all kind of move together, because what's happening there isn't that we're seeing them move around the sun, we're seeing our own motion, Earth's motion around the sun as we kind of lap them. So they're all further out, their years are a lot longer than ours. It takes a lot longer for them to go all the way around the sun. So we're seeing them move forward, we catch up with them, it looks like they're moving forward, and then for a little while it looks like they're moving backwards as we start to lap them. So that's kind of what's going on there. I like this kind of representation since you can really see the planets moving. Did anyone have any questions as you were working through that? Okay. Yeah. So that's what you, this data, that motion of the planets, was what the astronomers originally had when they were trying to figure out where Earth was in the solar system. And so the original idea, the geocentric model, postulated that Earth was the center of everything, so geo-Earth-centric. And in order for that model to work while looking at the paths of the planet with respect to the sun, we needed the planets to travel on epicycles. So you had all of the planets run circles around the sun, or circles around Earth, going around Earth in orbits. And then each of those planets is also on its own kind of little weird orbit that would loop it around so it could travel backwards. So in order for this to work, you kind of have to add more and more cycles, and it just gets really complicated really quickly. And that's this retrograde motion was one of the major reasons that astronomers shifted from the geocentric model to a heliocentric model, where all the planets are moving around the sun. So yeah, this is just another representation of that epicyclic geocentric model. Venus and Mercury are doing kind of weird things. Everything's going around the Earth, including the sun, but we have different amounts of weird loop-de-loops all these kind of planets are doing. So like if you look at Venus especially, it doesn't only have an extra loop on its orbit, it also, for some reason, isn't traveling in a circle, but in this kind of weird heart-shaped thing. So this was one of the major signs that astronomers noticed. We need to add all these epicycles, all these other weird things in order for the geocentric model to work. And so they started shifting towards ideas of a heliocentric model. So that was where helio is sun. So heliocentric places the sun at the center, and we no longer need to have epicycles to explain the retrograde motion of this planet. So retrograde was a word I heard thrown around in a couple of the groups. It's just retrograde is just that backwards motion that we're seeing as either the inner planets are lapping us or the outer planets are being lapped by us. So we can watch those planets shift direction as they orbit the sun, depending if they're inner planets or outer planets. We're going to see those shifts happen in different ways. So this is just another way to visualize that. The stars are far enough away and they're not orbiting the sun, so we don't see them move as we orbit the sun. So we can watch the path of an outer planet move in retrograde motion as we kind of go around the sun, and it moves around the sun more slowly. So this is just as we are moving, we see the planet projected on the background stars, and it does a little S shape. It moves forward, backwards for a bit, and forwards as we pass the planet. So that's the cause of the retrograde motion, and what you guys just saw as you watched the paths of the planets in that little animation. Okay, so now we get to talk about we take a little pause to talk about two of my favorite little weird science duo, and that's Tycho Brahe and Johannes Kepler. And so they talk about them very briefly in the book, but they don't give it nearly justice, especially to Tycho, because Tycho was crazy. So Tycho had this really great equipment. He was making the best astronomical measurements of the planets of anyone. He very detailedly plotted the paths of the planets throughout the sky throughout a year. But he was able to do this because he was fairly wealthy. He owned 10% of Denmark at one point. He also had a pet moose. Some places will say it's an elk, but because he was in Europe, elk and moose are the same. There's a weird word thing. So he had a pet moose, and he also liked to throw really extravagant parties. So sadly, at one of his extravagant parties, his pet moose got into his alcohol, got drunk, and fell down the stairs and died. So if you have a pet moose and you throw parties, make sure they stay separate. He also, you can kind of see it in this image, his nose looks a little funny because he got in a duel and he got his nose shot off, and had it replaced with either a gold or a silver one. There's talk about exhuming his corpse to figure out what his nose was made of. And he died when at one of his parties, he refused to get up and use the bathroom and his bladder exploded. So don't do that. But the point is, Tycho Brahe is like this crazy guy, but he had these really detailed measurements of the paths of the planet. And Kepler wanted those measurements because he was a very devout religious guy, and he wanted to show that the planets traveled on perfect circles and that he could understand God better if he could measure the orbits of the planets. So he had to work with Brahe to get his data, and eventually he got it when Brahe died at his party. So, and unfortunately, he did not show that the planets move in perfect circles. He showed that they move in ellipses. But I just love this image of Tycho Brahe throwing a giant party with his moose, and Kepler upstairs trying to study, and the broom telling him to shut up. But that's just my little, astronomers are weird people, and that has always been true. So once he got Tycho's data, Kepler was able to come up with 3 laws about planetary motion. The first one is that all planets move on elliptical orbits around the sun. So this is kind of an exaggerated view of that. You'll have ellipses like a circle, but instead of having one central point, you're kind of squishing it out into an oval. So the sun is at one focus, the other focus has nothing in it, and you get these kind of oval shapes that travel around that. The planet in this image is then that red dot. At the point where the planet is furthest from the sun, that's the aphelion. So furthest from the sun is aphelion, closest to the sun is perihelion. So we talked about, I threw those words in, I think, in this season's slides, but now we're seeing that it's because we're on these ellipses, there is a point where we're slightly further from the sun and a point where we're closest to the sun. You can also measure the eccentricity of an orbit based on how different the perihelion and the aphelion is. So less eccentric, you're closer to a circle. Eccentricity of 0 is a circle. An eccentricity of 1 is a parabola. And so a lot of comets travel on parabolic orbits where they come in and then they shoot off and they never come back. So that's an eccentricity of 1. All of the planets in our solar system have eccentricities pretty close to 0, but that just essentially determines how squished you are as an ellipse. So in this one over here, the eccentricity of 9, we would have one focus on this kind of black line and the other focus way over here. So the sun would be maybe on this black line, there would be nothing over here, and the planet would go on a really crazy orbit like this. And then when you are in, again, eccentricity of 0 is that perfect circle. So that's Kepler's first law. All planets are traveling around the sun on elliptical orbits. We can see that on Earth. This just shows the difference. When we're at aphelion, we're about 152 million kilometers from the sun, and when we're at perihelion, we're 147 kilometers from the sun, so slightly more distant, but not enough to really change the amount of radiation we get from the sun. And just again to point out that perihelion, the closest we get to the sun, happens on January 3rd, which is what we normally think of as winter, so not causing the seasons. Kepler's second law, then, is that the path of the planet sweeps out an equal area in equal time. So this is a little weird to think about. It just means that, like, if you had an obnoxious pizza that was an ellipse, you could make pizza slices that were all equal area, even if they didn't look like they were equal shapes, and those would represent the planet traveling the same distance. So that was poorly phrased. The idea is that if this area, this gray shaded area, is equal to this gray shaded area, then the planet, it takes the same amount of time for the planet to travel this distance as it does for the planet to travel this distance. So when the planet is closer to the star, closer to the sun, it's moving faster. When it's further away, it's moving slower. So when you're nearest to aphelion, you're moving slowest. When you're closer to perihelion, you're moving fastest. So we're sweeping out the same area in the same amount of time. And this is kind of visualizing this. All of those kind of weird pizza slices are the same size or the same area. So the planet is moving faster when it's close, and you're kind of getting a squished pizza slice, and it's moving slower when we're stretching out that pizza slice, but we have the same area. So this is Kepler's second law, is we sweep out equal areas in equal times, which, because we're on elliptical orbits, mean we move faster when we're closer to the star and slower when we're furthest from the star. I'm just gonna hit this point home. Ask you another question through the polls. So I've drawn a little kind of exaggerated orbit here. So we have another elliptical orbit, and I've got a little green planet going around a star. When is it going to be moving the fastest? Okay. So we've gotten, most of everyone has voted, and we're pretty much, oh, there we go, everyone's voted. We see A is when it's moving fastest, because A is when it's closest. So to sweep out that equal area, we have to be moving faster. C is actually going to be when it's moving slowest, because to sweep out that equal area, we don't have to be going very fast. So further from the star, we're moving slower. So now we have two laws. Planets move in elliptical orbits, equal areas and equal times. Kepler has three laws. So the last one, this one we're going to throw a little bit of math. The period squared is proportional to the semi-major axis cubed. So just to flashback, semi-major axis is half of your major axis. Sorry, I might not have said this. So the semi-major axis would be the center out. If we were a circle, the semi-major axis would be equal to the radius. But it's just the longer axis divided in half. So semi just means divided in half. So longer axis divided in half is your semi-major axis. And Kepler's law says the period, so the time it takes for the planet to go around one orbit, or the period squared, is proportional to the semi-major axis, so the radius essentially of that orbit cubed. The really nice thing is we can turn that proportionality into an equal sign as long as we are in our solar system. So as long as we use units of years for period, and AU, which we haven't quite talked about, AU is an astronomical unit. It's the distance from the Earth to the sun. So 1 AU is 1 Earth-Sun distance. So as long as we use those units, this becomes an equal sign. We don't have to worry about weird constants or other units. So period squared is equal to semi-major axis cubed. And we can see that this is true for everything in our solar system. If we plot the square of the orbital period in years and the cube of the semi-major axis, they all fall in a very nice linear relationship. With the further you are out, so if you have a larger radius of your orbit, the longer it takes for you to go around the sun. And Kepler was able to find all this just by watching the paths of the planets, which is pretty cool. Like, it's impressive. I don't think I could figure that all out. So I have one more polling question. So with this in mind, if we had a planet that was between Jupiter and Saturn and had a semi-major axis of 9 astronomical units, so 9 times the distance from the sun, what would the period be? So remember, our period squared equals semi-major axis cubed. P squared equals A cubed. Got one vote. Get a few more. We need to go back. Our equation, P squared, period squared, is semi-major axis A cubed. So we're mostly getting it. I threw a little bit of math at you kind of quickly. C is the right answer. 9 squared, I think, is 729. So that's our P squared, or no, 9 cubed, sorry. 9 squared is 81. 9 cubed is 729. So 9 cubed, we then take the square root of that. So to get our period, we take the square root of 9 cubed, and you get 27. So 9 cubed, all square rooted, gives you your period. Any questions? So those are Kepler's 3 laws. Planets travel in elliptical orbits. Sorry. We sweep out equal areas in equal times. So planets move faster when they are closest to their star. And at least for the solar system, P squared equals A cubed. So period squared equals semi-major axis cubed. Any questions about those 3 laws? So now we're gonna see how far we can get into Newton's laws and just kind of wrap up here. We got about 10 minutes left, I think. So Newton also has 3 laws. I guess these early physicists and astronomers liked having 3. There's the law of inertia, which is just an object at rest tends to stay at rest. An object in motion tends to stay in motion. So that one, maybe you've heard before. I think it gets a little counterintuitive because we live on Earth and there's a lot of air resistance and friction that do slow things down. So those are our outside forces. If you act on something with an outside force, it will stop or it will start. But otherwise, inertia, every object will be, an object at rest tends to stay at rest, an object at motion tends to stay in motion. The second law is the law of momentum. And that just tells us that the change in motion of a body is proportional to the direction of the, to the direction of the force acting on it, to the strength and direction of the force acting on it, sorry. So if you push something harder, it will change its motion more, essentially. The bigger the force, the bigger the change in motion. And the last law is that for every action, there is an equal and opposite reaction. So this is kind of, if I push a box, the box is also pushing back at me, even though we end up, we're going to be moving depending on our masses and the strength of my push, that'll change how we move, but every force has an equal and opposite reaction force. So we won't be using those much throughout this. There's kind of two important things in Newton's 3 laws that we want to pay attention to, and that's that we can kind of change angular momentum by changing our shape. And so if we look at a figure skater, when they have their arms spread out, they're moving slower. When they bring their arms in, they start spinning faster. And this is really similar to Kepler's 3rd law. So that p squared and a cubed is all just kind of an angular momentum. We're changing momentum by changing our shape. And by doing that, we change the speed that we spin around. So Mercury has a very small radius, so it spins really fast. Jupiter has a really large radius, so it spins slowly. So that Kepler's 3rd law, that p squared equals a cubed, is actually because of the conservation of momentum, Newton's 2nd law. And we're changing the shape, and we get changes in speed. So it's just, again, and kind of similar on that Kepler's 2nd law. As the planet gets closer, we're again changing shape, we change speed. We're similar to that ice skater pulling their arms in or extending their arms out. If you have a spinny chair and some weights, I meant to bring in weights and I didn't, I might try next class. You can actually do the same thing on a spinny chair. You can spin yourself around, and by pulling your arms in, you'll start spinning faster. And that's the exact same thing that's happening to the planets. If they are closer in, if we have a smaller radius, we're moving faster because we're changing our angular momentum by changing the shape of our orbit. So we're running out of time, so I don't want to get too far into this, but the last big thing that Newton did that's going to be very important for this class is that he came up with the universal law of gravity, which tells us how the planets hold themselves in orbit. The thing I think is kind of crazy is that Newton's goal was to understand why the planets orbited the sun the way they did. And in order to figure that out, in order to come up with his equation, he ended up inventing calculus. So, you know, no big deal. He just wanted to understand the planets, and in the process of doing that, accidentally invented calculus. So you can blame Newton for having to take calc in high school. But the big thing that was really kind of crazy that he came up with is that the same force that pulls an apple that falls to the earth down to the earth, that's the same force that holds the earth in orbit around the sun. So gravity works on a lot of different scales. It holds us on the earth. It also holds the earth around the sun. It holds the moon in orbit around the earth. All of these things are true, and they're all caused by gravity. He also was able to come up with this equation, which we will visit a few times, is that the force of gravity is equal to big G, this is the universal gravitational constant, times the mass of the two objects divided by the distance between them. And what's kind of crazy about this is that it means everything is pulling on each other. So even if you're not in Walla Walla, I am gravitationally pulling on you. It's just not very large because we're so far apart. And our masses are pretty small. And when you compare the masses of us to the masses of the Earth, we're a lot less, so we get overwhelmed by that gravitational pull of the Earth, and that's what we feel. But gravitationally, it doesn't matter how far away something is, we are being pulled on it through this law of gravitation. The other thing I like to think about, we can talk about this more when we get into Earth's orbit, but if you want to weigh less. What you're measuring when you weigh yourself is the force of gravity. So if you wait till the moon is directly overhead, you'll actually be being pulled upwards by the moon slightly and pulled down by the earth. So you get very, 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 very small, pretty much unmeasurable changes in your weight when the moon is directly overhead, because it's actually pulling you up through the laws of gravity. You're being pulled towards the moon and down towards the earth. And the earth just wins because it's bigger and we are closer, and that r squared is pretty important. Okay. We're close to wrapping this up. The last thing, and this was all about, in people who did the reading quiz, I asked you a little bit about satellites and how they're able to stay in orbit even though they're being pulled by Earth. And it's because they're traveling, they're still being affected by gravity. They're just falling around Earth fast enough that they never actually hit the Earth. So this is kind of to try to show this. We're going to launch a cannon off Earth, and when I don't launch it, when I only use one bag of gunpowder, it falls off the Earth, but it kind of curves around a bit first. If I launch my cannon with enough energy, so I'm doing 3 bags of gunpowder, whatever that means, it'll keep falling around the Earth and it'll never actually land. So satellites are the same thing. We launch them into space and they're continuously falling around the Earth, but they're falling at a rate that they never actually hit because the Earth is curving away from the satellite's path at the same rate as it is falling. So this is how we keep things in orbit around the Earth. They're still being affected by gravity. They're still being pulled down to the Earth. It's just they're falling at a rate that they never actually crash into Earth. So anything that's in orbit, the moon is falling around Earth. All of Elon Musk's SpaceX satellites are falling around Earth and causing mischief. They just never hit because the Earth is curving away from us, fast and curving away from their path at the same rate that they are falling. So this is kind of where we're going to have to wrap up today. We pretty much got through everything. So